Hello everybody, welcome back to a new video here on this channel. In this video we're going to solve a problem by the name of some noons. So in this problem, a man is flying from Seoul to St. Petersburg on December 21st. He flies with a height of 11 kilometers. During his highest latitude or on the longitude of his highest latitude, it's supposed to strike noon. Will he be able to see the sun? Now, in the beginning, it looks like some kind of oxymoron here. Of course, you're supposed to be able to see the sun during noon, but it's what most people would say, right? But it's not always the case. So first off, to solve this problem, we have to draw the diagram of the problem. This is what I did. It's a rough sketch of the Earth and the case that we're taking, the man flying from Seoul to St. Petersburg. Now, as you know, planes try to maximize their efficiency, and one way to do it is through flying through great circles of the Earth. And here they fly by a great circle between two great circles, which is right here and right here. They fly this great circle here, creating a spherical triangle. Where one outer angle is 90 degrees minus the latitude of Seoul, and another one is 90 degrees minus the latitude of St. Petersburg, and the third one being this theta here. And the inner angle facing this theta is the delta lambda, or in this case, the difference in longitudes of these two places. Since it's a spherical triangle, we can then apply the cosine law here, right here, and by doing the math and applying it, we'll find that this theta is equal to 58.162 degrees. Now, if you're wondering about this phi p and this phi s and this delta lambda, you can just search them up on Google. Just search Seoul coordinates and St. Petersburg coordinates and you'll be there. Now, if you see in this diagram that theta isn't the only unknown angle here, there's also alpha. Now, how do you find alpha? Because as I stated earlier, this is a spherical triangle. Therefore, this sinus law must also apply here for this delta lambda and theta and this alpha and 90 degrees minus phi p. This alpha here is the azimuth from north to west of the man's flight from Seoul. And by using the sine law over here, we will find that this alpha is equal to 35.862 degrees. Now, if we were to zoom in to this triangle, we will also see this point here, this H, or the highest point here. It's the point which is highest latitude or the closest to the North Pole. And one of the characteristics of that is that it creates a 90-degree angle with this line here. So this line is a changing slope. It has a 90-degree angle. When it has a 90-degree angle, it's at its highest point right here at H. Here. Now, this creates another great triangle here, a spherical triangle right here, this one. Therefore, we can also then apply the sine law right there. So we're using this one, the 90 degrees minus the phi h, which is facing alpha, and this 90 degrees here, which is facing 90 degrees minus phi s, or the latitude of Seoul. And we'll find that the phi h, or the latitude of the highest point, is equal to 72.930 degrees. So it's quite close to the North Pole. And we also know that this man doesn't fly on ground level, like obviously. So he flies with a height, and we can model this height right here. Because of this height, the latitude we found earlier, it also has to be corrected with this change in latitude because of his height. Now, what is this change in latitude? As you see in this diagram, this delta phi here is equal to cosine the arc cos of this radius of the Earth and radius of the Earth plus its height, which will make it 3.360 degrees. Therefore, we have to add this change here to the one we found earlier, making his corrected latitude to be 76.263 degrees. Now, what does that tell us about if he's able to see the sun or not? Well, for anyone at any latitude, what he's able to see is this corrected latitude plus 90 degrees all the way until the corrected latitude minus 90 degrees. Or since this is the corrected latitude plus 90 degrees is over 90 degrees, we can say that he's able to see up to 90 degrees until negative 13.707 degrees. So this is like the range in which things with this declination he can see. Now, what does that tell us about the sun? You see that December 21st is a relatively special day. The sun is at its lowest declination of negative 23.5 degrees, and we see that this declination is less than the minimum declination which is visible to him at that point. Therefore, we can say that the sun is not in sight despite it being noon. Okay, this is all for this video. Hope you enjoyed and you learned something new. Thank you.